rectal swab taken or donate a poo sample. So these people say no. People are very protective of their own poo, apparently. So the numbers get lower, but you still get a significant number of people transmitting these things. And of course, we do know that E. coli within a family will spread around. So this is a lovely family. For 3 years, this family were swabbed periodically for what E. coli they were carrying around in their feces. And basically, the overlay in the middle, which is everything multicolored, just shows what's happening. Each color represents a different type of E. coli, and you can basically see that at any given time, they've all kind of got anything. So it's just sharing around amongst the family. And what have we got here? We've got a mother and a father at the top. We've got a son, 2 daughters, and we've got a dog, right? They swabbed the dog as well. He was the only one who didn't have to bend over for the process. But basically, what this shows is that if you live in a close-knit group, this works in schools as well, apparently. The data is not so strong. If you're in a close-knit group, you will share these normal flora E. coli. These people are not getting ill, okay, but this is just normal flora. But we know that that normal flora can be the opportunistic infection of the future, the silent killer, if you like, if this is antibiotic-resistant normal flora. So if the mother goes away on a business trip to India and picks up some E. coli carrying an NDM1 massive multi-drug resistance thing, then she could spread it around the family. If the dog, which presumably the dog's the only member of the family that would do this, but if the dog goes out and eats a cow pat in the local farmer's field, maybe the kid would as well, I don't know, but if the dog does that, then maybe the dog can bring that E. coli from the animal into the household. So these are kind of issues. So if we assume that there's a potential, at least, for animal E. coli to influence the home, what's going on in animals? Now, my veterinary colleagues, I'm fairly new to the farm animal vet side, but as I said, my wife's a small animal vet, so I know a fair bit about that. But basically, antimicrobial resistance is not a significant problem, certainly in large animal practice, mainly because the animals don't live long enough to get the sorts of long-term debilitation-related infections that you might see in humans. In animals, in small animals, you might see that more. So orthopedics, the cat that's being run over and stuck back together again. There may be the issues around opportunistic infections in a similar way to we see in humans. But generally speaking, there are not animals falling down dead as a result of antimicrobial resistance. It's not considered or perceived to be a problem by the profession or by farmers that this is a problem in terms of health and well-being. Okay? That's not to say they don't believe it's a problem in other regards, and we'll talk about that. Now, then you get onto the blame game, which is like who uses the most antibiotics. Now, if you use it by weight, then it's used more in farming than in human medicine. If you use it by numbers of doses, then it's used more in human medicine than in farming. I don't want to play that game. We all use antimicrobials, and we're all responsible for the use of antimicrobials. So let's just accept that we all need to do something about it. The problem with farming, and I don't know, this may be true also, but to a lesser extent in human medicine, is we don't really understand the drivers. Why do people use antimicrobials in the way they do? How much is used? Well, actually, it's quite difficult to get this data. So this is a study that was actually based on data in 2014, and it shows that in the UK, for every kilogram of meat, actually the data was from 2011, it was published in 2014, we use 51 milligrams of antimicrobial for every kilogram of meat that's on your plate. That doesn't mean there's 51 milligrams in a steak. It just means that through its lifetime, that animal has had that much. Now, this is very variable. In pigs and poultry, it might be 150 milligrams per kilogram, because those animals live in confined environments, they're more prone to transmissible infections, and therefore they're more likely to need antibiotic therapy. So they get more drugs. In species that tend to live outside in the fresh air, away from each other, like sheep, there's virtually no antibiotic use. Cattle are kind of low for beef, a bit more for dairy because they're a bit more intensive. It kind of works on that basis. The worst is game bird production. Apparently there's something like 7 grams of antibiotic for every kilogram of pheasant if it's being farmed. And obviously fish farming is a big problem as well. Apparently in North America, if you eat a bit of salmon, that salmon will have had 7 times its own body weight in antibiotics in its life. So, there's a lot of antibiotic used out there. Interestingly, as part of the 5-year plan that Neil talked about, recently it's been announced that they're going to set a very stringent limit on the average amount of antibiotics used in food production in the UK, and they've set that limit as 50 milligrams per kilogram. So that's a very ambitious target, I think, based on that. But it's clearly we need to think about less as well. In terms of antimicrobial resistance, what's carried around? Well, surveillance is pretty rubbish. There's a lot of funding being pulled from organizations that were involved in this during the last recession. Maybe we're in another one, I don't know. But generally, resistance is rare in pathogens, disease-causing organisms, but relatively common in E. coli, in the guts of these animals. So again, we're coming down to this. Again, the animals that use more antibiotics then have more resistance. So pigs and poultry, more resistance because they use more antibiotics. Now, when we think about transmission of antibiotic resistance from animals to humans, I want to start off by thinking about food poisoning. Because if anybody ever argues to you, oh, bacteria, they don't get transmitted from animals to humans, perhaps is not one of the 200,000 people a year who get Campylobacter food poisoning in the UK. Because, of course, you can't get that. Well, you might get it as a secondary infection from another family member, but generally, it's a primary infection from a source of meat, usually chicken, the dodgy kebab on the Friday night. And that's because, of course, they're carried in the feces of chickens. And salmonella and enteropathogenic E. coli in beef cattle are other issues in this regard. So we know damn well that even though you tell people to cook their food, and even though we tell them to wash their hands, and we tell them not to rub their steak on their salad before they've cooked it, all of those things fall down in reality because people are getting these infections. They happen. And because all of these bacteria come from the feces of animals, which contaminate the carcass during slaughter, of course, E. coli are going to contaminate the carcass during slaughter as well. All these animals carry E. coli as well as these pathogens, and therefore you will be eating E. coli in the food that you eat. It's going to happen. Nobody could argue that it's not. The argument really is what's the consequence of that, okay? Because normal E. coli from an animal is not going to make you feel ill. You're not going to know it's happened. But is it going to have any long-term consequence to you? And that's the argument, really. Let's assume it does have a consequence. So let's assume that when you get Campylobacter, it's so serious that you need a course of antibiotics. Now it's a problem for you if that Campylobacter is resistant to antibiotics because the animal that it came from had been given too many antibiotics. That's a problem. So let's assume it's a problem. We need to reduce the amount of antibiotic usage. And of course, we know that that's happening in human medicine, but it's also happening in veterinary medicine and farming as well. And that's mainly being driven by the producers, the milk producers in this case of this article about Arla, but also the retailers. And Bristol Vet School colleagues are working with the retailers to try and implement this and make it happen. And it's been driven by consumers, basically. It's been driven by the desire to put a big stamp on a bottle of milk that says it's got no antibiotics in it. Frankly, that's what it's all about. And therefore, as people become more aware of the problem, the retailers become more aware of this issue. And so that gives a scope for research and development activities in this area. And my colleagues at Bristol Vet School, led by Kristen Ryer, have set up an organization called AMR Force, which is a hugely wide-ranging organization dealing with all sorts of different areas. And we've got projects looking at the idea of understanding what medicines are actually used on farms. So we know what's being prescribed, just about, but of course, unlike in human medicine, you tend, as a farmer, you get your antibiotics in bulk, and then you're responsible for deciding which animal gets it when, as part of a health plan that's agreed with your vet. But we don't really understand about compliance with that herd. Are they using the right amount of antibiotic? Are they using the wrong amount of antibiotic? Are they using the wrong antibiotic in the wrong situation? Ultimately, nobody's watching them all the time to see that they're doing it correctly. So actually what we're doing as part of this area is we're actually watching them a little bit. One of the PhD students in the group, Gwen, is basically rummaging through their bins to find out what antibiotic bottles they're throwing away. and with a view to understanding what they genuinely are using versus what they might be supposed to be using. We're interested, of course, in trying to encourage responsible use. So we're interested in the idea that farmers actually know what they're doing wrong quite a lot of the time, and when they get together, they can actually work out the solutions to some of these problems and deal with it. Once there are changes that are going on farms, can we actually understand what's happening to antimicrobial resistance? So is there any way that we can see whether or not resistance changes? And so on and so on. I've got no time to talk about all the details of everything that's going on, but they've got a Twitter feed, and you can look them up on the internet if you're interested in what they're doing. But one of the real key things that AMR Force and the University of Bristol farm animal practice has delivered is a reduction in antibiotic usage in farming. So this is critically important antimicrobial usage, and it doesn't matter what the scale is, because at the end here, in 2015, it's 0. They don't use any critically important antimicrobials, so third, fourth generation cephalosporins, fluoroquinolones, long-acting macrolides, they're not used in the large animal practice in dairy. Now, that's an exemplar to the rest of the profession that it can be done. They've shown quite clearly that this doesn't have a negative impact on animal health or well-being or production. It has to be done in conjunction with improving management practices, and has to be done in conjunction with farmers and the way that they work. But it's a realistic proposition that they could reduce usage and have done. I would argue, however, that just reducing the usage of critically important antimicrobials like those third and fourth generation cephalosporins doesn't necessarily mean that antibiotic resistance will go away. Because, antibiotic resistance is, as I said earlier, encoded on plasmids, bits of DNA, which carry resistance usually to multiple things. In this case, not just antibiotics, well, any one of these antibiotics, tetracycline, amoxicillin, fluoroquinolones, any of these would select for this plasmid, and it would therefore give resistance to all of the others. But not just that, but also things like disinfectants, resistance to those are carried on these plasmids. Resistance to heavy metals are also carried on these plasmids. So this whole idea that if you use or the environment is contaminated with any one of these things, then it will potentially select for this plasmid, which will give resistance to all of these things. So reducing one won't necessarily solve the problem. This is also true in human medicine, but it's particularly true in a farm when they're often using heavy metals as growth promoters or as disinfectants. They're often using lots of disinfectants, spreading them around, foot baths, all sorts of things going on. So we want to know whether or not this is a problem. Now, of course, there are many different ways that normal flora could be affected by farm animals. One is eating food. I've already talked about that. But let's say that's controversial for E. coli. It certainly is. But maybe if you go walkies across through a herd of cows, you might think, oh, we're in the lovely countryside. I'll go and eat my sandwiches now. You don't wash your hands. Maybe you take your boots off so you can air your feet. Your boots are covered in poo. Now your hands are oh, it's all right. I'm in the countryside. Everything's clean. You eat your sandwiches now. Potentially you're contaminated with the E. coli and colonized. Or has anybody let their dog lick their face? What was it licking before it licked your face? Yeah, your dog might go walkies through the cows, it might roll in the cow pats and so on. So there's many different ways that these bacteria can move in. So I guess the question is, does it happen? Now, I think I'll just summarize rather than going into the detail given the audience, and I'll just say that actually we thought that it must be obvious that resistant organisms in animals move into humans. But actually, it seems like the organisms that we find in humans are not necessarily the same as the ones in animals. So there's a little bit of overlap, where some of the resistant bacteria that we see in animals are the same as the resistant bacteria we see in humans, but actually not that many. Okay? So you can use all sorts of clever genomics technologies where you sequence the entire genome of the organism, and you go, oh, does that one, is it the same as that one? That one's come from a cow, that one's come from a human, that one's come from a steak. Are they the same thing? And actually, there's lots of studies that have been done like this, and generally the finding is that generally they're not the same. Generally,